Hi, my name is Scott. I'm from the Economics Tutoring Center, and today we'll be conducting a hypothesis test for the difference of two means. So please make sure to check my notation and language use with your instructor because it may vary. Okay, so we have a question here. It says, we have one sample with a mean of 48 and a standard deviation of 5.2. We have another sample drawn from a different population with a mean of 48.6 and a standard deviation of 5.4. Both samples have 35 observations. We want to test the hypothesis that the means of both populations are the same using a significance level of 0.05. And it tells us there are 67 degrees of freedom because, as we'll find out, the formula for degrees of freedom for a test like this is pretty complicated. So sometimes you'll just be given the number. So the first thing we might want to do is we're testing a hypothesis, so we want to write down what the hypotheses are. And so it tells us the hypothesis that the means of both populations are the same. So let's just say mu1 is the mean of the first population, mu2 is the mean of the second population. And I'm actually going to write this another way, an equivalent way, that will help when we're calculating the test statistics. So you can just subtract mu2 over to the other side, say that their difference is 0. Our alternative hypothesis then is that mu1 is not equal to mu2, or that their difference is not equal to 0. And this is called a hypothesis test for the difference in two means. And the test statistic, well, first of all, we need to identify if we are doing a t or a z test. And because it tells us we have a sample with a standard deviation of 5.2 and another sample with a standard deviation of 5.4, we have sample standard deviations. That means we want to use a t-test. The formula for the test statistic for the difference in two means is, so you take the sample average from the first sample minus the sample average from the second sample, you subtract the hypothesized difference, and you divide by the standard error. I'll write what the formula for standard error is on the next slide here, because it takes up some space. But that's the general idea of the test statistic for this one. And then we already know a few of these numbers, so x bar 1 is the first sample average of 48. And usually you choose group 1 just to be the first one in the question, group 2 to be the second sample in the question. So x bar 2 is 48.6. This d with the 0 subscript, like I said, that's the hypothesized difference. In this case, it's 0, because if you look at the hypotheses, we have that the difference, our hypothesis is that the difference is equal to 0. So this is why 0 is the hypothesized difference. And that's often the case. A lot of times for these tests, you'll have 0 for your hypothesized difference. Not always, though. So, again, same question. I'll rewrite the t formula, but I'll actually write out standard error this time. So these are the same. A standard error is, remember we have two samples, so we have the standard deviation of sample 1 squared divided by the sample size of sample 1. Then we add the same thing for sample 2, standard deviation squared divided by sample size. That's our standard error from the formula before. And we can pick out what these numbers are too. So S1 is 5.2. Right here it tells us the sample standard deviation, sorry. S2 is 5.4, it tells us that here. And then N1 and N2 are actually the same in this question. It tells us both samples have 35 observations, so both those numbers are 35. If you notice, that will mean we have a common denominator in this formula. So you could simplify it a little bit by combining these fractions. You don't have to do that though, so we can just plug these numbers straight into the formula. So let's do that. We have our t statistic is equal to, so remember x bar 1 was 48, x bar 2 was 48.6, so those were from the last slide, or you can just see them up here. The hypothesized difference was 0. Then we divide by standard error, so standard deviation 1 was 5.2. We square that number, divide by 35. Then we do the same thing for sample 2. Standard deviation was 5.4. Square it, divide by 35. And then if you plug this whole big number into your calculator, you should get a test statistic of negative 0.4735 approximately. So now we need to draw a conclusion now that we've found the test statistic. So I'll remind you what that number was. So we got negative 0.4735 as our test statistic. We need to find a critical value. So remember, we do that from the t-table or a t-calculator. Our alpha is 0.05, our level of significance. And because this is a two-tailed test, we're going to want to divide alpha by 2, 0.025. And it's a two-tailed test because we had, remember, our null hypothesis has an equal sign in it. And whenever you have an equal sign in your hypotheses, that means it's a two-tailed test. Our degrees of freedom was 67. And like I said before, the formula for that is complicated, and that's why you'll typically be given the degrees of freedom for a test like this. So if you use that information and you look on the t-table or use a t-calculator, you'll get that the critical t-value is plus or minus. Now the reason why I have plus or minus here is also because it's a two-tailed test. That means we'll have two rejection regions. So if you draw the t-distribution, looks something like this. This is the positive critical t-value over here. This is the negative critical value, and that means that here and here are our rejection regions. Okay, so finally we'll make the conclusion. So our t was negative 0.4735. Our critical t value was plus or minus. And the decision rule for a test like this is, okay, if the absolute value of your test statistic is less than the critical t-value, and I put this absolute value to say we want the positive critical value. This means you fail to reject the null hypothesis, and then the opposite case is, well, if your test statistic is greater, or the absolute value is greater than or equal to your critical value, you reject the null hypothesis. So if we look at this specific one, the absolute value of our test statistic is positive 0.4735, and that is less than our critical value. So that means we reject the null or we fail to reject the null hypothesis. And remember, the null hypothesis was that these two means are the same, or that their difference is 0. So the fact that we failed to reject the null hypothesis means that we did not find statistically significant evidence to disprove this null hypothesis. So we would conclude that the two population means are similar or the same.